transformer loading should always be computed as the sum of Vphase multiplied by Iphase, rather than summing the individual loads. The reason for this is that individual loads may lack balance, and summing them won't provide the accurate total load. Consider a scenario where the load perceives it's receiving 208 multiplied by I volt amps, but the transformer registers delivering 2 multiplied by 120 multiplied by I volt amps. This discrepancy arises because the load is connected line to line, while the transformer is connected in a Y configuration. The line-to-line voltage measures 208 volts, whereas the phase-to-neutral voltage is 120 volts. Consequently, the load perceives only the phase-to-neutral voltage, leading it to underestimate the actual power it's receiving. Conversely, the transformer detects the line-to-line voltage, leading it to overestimate the power it's delivering. Hence, the significance of computing transformer loading as the sum of Vphase multiplied by Iphase. This method ensures an accurate total load calculation, facilitating appropriate transformer sizing. Even in scenarios where loads are balanced, calculating transformer loading using the sum of Vphase multiplied by Iphase remains preferable. This approach offers greater accuracy and provides a more precise understanding of the actual load imposed on the transformer. This is a critical consideration, often overlooked, yet capable of substantially influencing transformer sizing decisions. When dealing with three-phase systems, particularly Y-connected systems with unbalanced loads, the potential for error in transformer loading calculations becomes significant. A common mistake is to simply add up the individual loads without considering the phase relationships and voltage differences. This can lead to a substantial underestimation of the actual load on the transformer, potentially resulting in premature failure or inefficient operation. The Vphase multiplied by Iphase method directly addresses this issue by taking into account the voltage and current on each phase. This provides a more accurate representation of the total power being delivered by the transformer. To further illustrate the importance of this method, let's delve into a more detailed example. Imagine a three-phase Y-connected transformer supplying power to three separate single-phase loads. Load 1 is connected between phase A and neutral, drawing 10 amps at 120 volts. Load 2 is connected between phase B and neutral, drawing 15 amps at 120 volts. Load 3 is connected between phase C and neutral, drawing 20 amps at 120 volts. If we were to simply add up the individual loads, we would arrive at a total load of 10 amps plus 15 amps plus 20 amps, which equals 45 amps. Multiplying this by the phase to neutral voltage of 120 volts, we get a total volt-amp load of 5,400 volt-amps. However, this calculation is incorrect. It fails to account for the fact that the currents in each phase are not in phase with each other. To accurately calculate the total load, we need to use the Vphase multiplied by Iphase method. This involves calculating the volt-amps for each phase separately and then summing the results. For phase A, the volt-amps are 120 volts multiplied by 10 amps, which equals 1200 volt-amps. For phase B, the volt-amps are 120 volts multiplied by 15 amps, which equals 1800 volt-amps. For phase C, the volt-amps are 120 volts multiplied by 20 amps, which equals 2400 volt-amps. Summing these values, we get a total volt-amp load of 1200 volt-amps plus 1800 volt-amps plus 2400 volt-amps, which equals 5400 volt-amps. In this specific example, the two methods yield the same result. However, this is only because the loads are purely resistive and the phase-to-neutral voltage is the same for all three phases. In more complex scenarios, where the loads have reactive components or the phase-to-neutral voltages are different, the difference between the two methods can be significant. Consider a scenario where load 1 is a resistive load drawing 10 amps at 120 volts. Load 2 is an inductive load drawing 15 amps at 120 volts with a power factor of 0.8, and load 3 is a capacitive load drawing 20 amps at 120 volts with a power factor of 0.9. In this case, simply adding up the individual loads would be grossly inaccurate. We would need to calculate the real power and reactive power for each load separately and then sum the real powers and reactive powers to obtain the total real power and reactive power. From these values, we can then calculate the total volt-amps. The Vphase multiplied by Iphase method automatically takes these factors into account, providing a much more accurate result. Furthermore, it is crucial to consider the transformer's nameplate rating when determining the appropriate size. The nameplate rating specifies the maximum volt-amp capacity of the transformer. It is essential to select a transformer with a nameplate rating that is greater than or equal to the calculated total load. However, it is generally recommended to choose a transformer with a slightly higher nameplate rating to account for future load growth and potential overloads. In addition to accurately calculating the transformer loading, it is also important to consider other factors such as the ambient temperature, altitude, and cooling method. These factors can affect the transformer's ability to dissipate heat and can impact its overall performance and lifespan. For example, at higher altitudes, the air is thinner, which reduces the effectiveness of air cooling. In such cases, it may be necessary to direct the transformer or use a different cooling method such as oil cooling. The National Electrical Code, or NEC, provides guidance on the proper installation and sizing of transformers. NEC Section 450 covers transformers in detail, including requirements for overcurrent protection, grounding, and ventilation. It is essential to consult the NEC and any applicable local codes when installing or sizing a transformer. Understanding transformer connections is also crucial for accurate loading calculations. Transformers can be connected in various configurations such as Y-Y, Delta-Delta, Y-Delta, and Delta-Y. The connection type affects the voltage and current relationships between the primary and secondary windings, which in turn impacts the loading calculations. For example, in a delta-Y transformer, the line voltage on the delta side is equal to the phase voltage, while the line voltage on the Y side is equal to the square root of 3 times the phase voltage. Similarly, the line current on the delta side is equal to the square root of 3 times the phase current, while the line current on the Y side is equal to the phase current. These relationships must be taken into account when calculating the transformer loading. Moreover, harmonic currents can significantly impact transformer loading. Harmonic currents are non-sinusoidal currents that can be generated by nonlinear loads such as electronic devices, variable frequency drives, and lighting systems. These harmonic currents can cause increased heating in the transformer windings and core, which can reduce its lifespan and efficiency. To mitigate the effects of harmonic currents, it may be necessary to use harmonic filters or to select a transformer that is specifically designed to handle harmonic loads. In addition to harmonic currents, voltage imbalances can also affect transformer loading. Voltage imbalances occur when the voltages on the 3 phases are not equal. This can be caused by unbalanced loads, voltage drops in the distribution system, or problems with the utility power supply. Voltage imbalances can cause increased heating in the transformer windings and can also lead to reduced efficiency and premature failure. To mitigate the effects of voltage imbalances, it is important to balance the loads as much as possible and to ensure that the distribution system is properly designed and maintained. Furthermore, it is important to regularly inspect and maintain transformers to ensure that they are operating properly and efficiently. This includes checking the oil level, inspecting the bushings and connections, and testing the insulation resistance. Regular maintenance can help to identify and correct potential problems before they lead to more serious issues. To summarize, accurate transformer loading calculations are essential for ensuring the reliable and efficient operation of electrical systems. The Vphase multiplied by Iphase method provides a more accurate representation of the total load compared to simply summing the individual loads, especially in systems with unbalanced loads or non-sinusoidal currents. It is also important to consider other factors such as the transformer's nameplate rating, ambient temperature, altitude, cooling method, and harmonic currents. Consulting the NEC and any applicable local codes is crucial for proper installation and sizing. Regular inspection and maintenance can help to ensure the transformers are operating properly and efficiently. When sizing a transformer, it's not just about the immediate load. Anticipate future growth. Will new equipment be added? Will the building be expanded? Account for these possibilities by adding a safety margin to the calculated load. A common practice is to size the transformer to handle at least 125% of the current load. This prevents overloading and ensures the transformer operates within its design limits, extending its lifespan. Power factor correction plays a vital role in transformer efficiency. A low power factor means the transformer is supplying more apparent power, or voltamps, than actual power, or watts. This increased current flow leads to higher losses in the transformer windings and reduces its overall capacity. By installing power factor correction capacitors, you can improve the power factor, reduce the current flow, and free up transformer capacity. Regularly monitor the transformer's operating parameters such as voltage, current, temperature, and oil level. This data provides valuable insights into the transformer's health and performance. Trends in these parameters can indicate potential problems, allowing you to take corrective action before a failure occurs. Consider using a transformer monitoring system that automatically collects and analyzes this data. The type of load connected to the transformer also influences its loading and performance. Linear loads, such as resistive heaters and incandescent lights, draw current that is sinusoidal and in phase with the voltage. Nonlinear loads, such as electronic devices, variable frequency drives, and LED lighting, draw current that is non-sinusoidal and out of phase with the voltage. These nonlinear loads generate harmonic currents, which can overload the transformer, cause excessive heating, and reduce its lifespan. If a significant portion of the load is nonlinear, consider using a K-rated transformer, which is designed to handle harmonic currents. The ambient temperature around the transformer affects its ability to dissipate heat. High ambient temperatures reduce the transformer's capacity and can lead to premature failure. Ensure adequate ventilation around the transformer to remove heat. If the ambient temperature is consistently high, consider using a forced air cooling system or a liquid-filled transformer. The altitude at which the transformer is installed also affects its cooling performance. At higher altitudes, the air is thinner, which reduces its ability to remove heat. Dare the transformer's capacity if it is installed at a high altitude. Consult the transformer manufacturer's specifications for daring factors. Proper grounding is essential for transformer safety and performance. A properly grounded transformer provides a low impedance path for fault currents, protecting equipment and personnel from electrical shock. Follow the grounding requirements specified in the NEC and local codes. Surge protection devices, or SPDs, protect the transformer from voltage surges caused by lightning strikes or switching transients. Voltage surges can damage the transformer windings and insulation, leading to failure. Install SPD on both the primary and secondary sides of the transformer. The transformer's insulation is critical for preventing short circuits and ground faults. Regularly test the insulation resistance to ensure it is within acceptable limits. Low insulation resistance indicates that the insulation is deteriorating and needs to be replaced. Oil-filled transformers require regular oil testing to ensure the oil is free of contaminants and has adequate dielectric strength. Contaminated oil can reduce the transformer's cooling capacity and insulation strength, leading to failure. Sample the oil periodically and send it to a laboratory for analysis. Bushings provide insulation and support for the conductors entering and exiting the transformer. Inspect the bushings regularly for cracks, chips, and other damage. Damaged bushings can lead to flashovers and short circuits. Connections must be clean, tight, and corrosion-free to ensure good electrical contact. Loose or corroded connections can cause overheating and voltage drops. Regularly inspect the connections and tighten them as needed. The NEC requires overcurrent protection for transformers to protect them from overloads and short circuits. Overcurrent protection can be provided by fuses or circuit breakers. Size the overcurrent protection devices according to the NEC requirements. Transformers generate heat as they operate. Adequate ventilation is essential for removing this heat and preventing the transformer from overheating. Ensure that the transformer room is well ventilated and that there are no obstructions blocking airflow. Consider using a forced air cooling system if natural ventilation is insufficient. Regularly inspect the transformer for signs of overheating, such as discolored paint, bubbling insulation, or a burning smell. Overheating can damage the transformer and lead to failure. Keeping the transformer clean prevents dust and debris from accumulating on its surfaces, which can reduce its cooling capacity and insulation strength. Regularly clean the transformer with a vacuum cleaner or a soft cloth. Avoid using water or harsh chemicals, which can damage the transformer's insulation. Accurate record keeping is essential for transformer maintenance and troubleshooting. Keep records of all inspections, tests, repairs, and maintenance performed on the transformer. This information can be used to track the transformer's performance over time and to identify potential problems. If a transformer fails, conduct a thorough investigation to determine the cause of the failure. This will help prevent future failures and ensure that the replacement transformer is properly sized and installed. Consider consulting with a qualified electrician or engineer to troubleshoot transformer problems. They have the knowledge and experience to diagnose and repair transformer issues safely and effectively. Furthermore, consider the transformer's inrush current. When a transformer is initially energized, it draws a large surge of current known as inrush current. This inrush current can be several times higher than the transformer's normal operating current. Size the overcurrent protection devices to withstand the inrush current without tripping. Consider using slow-blow fuses or circuit breakers with a high instantaneous trip setting. The transformer's impedance is also an important factor to consider. The impedance is a measure of the transformer's opposition to the flow of alternating current. A lower impedance transformer will have a higher fault current, which may require larger overcurrent protection devices and a higher interrupting capacity for the switchgear. The transformer's voltage regulation is the change in secondary voltage from no load to full load. A transformer with good voltage regulation will maintain a relatively constant secondary voltage even as the load changes. Poor voltage regulation can cause problems with sensitive electronic equipment. Consider using a transformer with a tap changer, which allows you to adjust the secondary voltage to compensate for voltage drops. The transformer's efficiency is the ratio of output power to input power. A more efficient transformer will waste less energy and save money on electricity bills. Consider using a high-efficiency transformer, especially for applications with continuous loads. The transformer's noise level can be a concern in some applications, such as hospitals, schools, and office buildings. Consider using a low-noise transformer or installing sound barriers to reduce the noise level. The transformer's location should be carefully considered. Choose a location that is easily accessible for maintenance and inspection, has adequate ventilation, and is protected from the elements. Avoid locating the transformer in a flood-prone area or near flammable materials. Finally, safety is paramount when working with transformers. Always de-energize the transformer before performing any maintenance or repairs. Wear appropriate personal protective equipment, such as gloves, safety glasses, and arc flash protection. Follow all safety procedures and guidelines. Remember that transformers are essential components of electrical systems, and proper sizing, installation, and maintenance are crucial for ensuring their reliable and efficient operation. By following these guidelines, you can maximize the lifespan of your transformers and minimize the risk of failure.